Okay, so far we've done some chemistry with aromatic rings. This still falls under electrophilic aromatic substitution. But so far we've only made bonds to heteroatoms, right? We made bonds to nitrogens, we've made bonds to sulfur, made bonds to iodine and chlorine and bromine. We haven't made a carbon-carbon bond yet, and that's the best kind. So let's do that. The Friedel-Crafts reaction. If I take tert-butyl chloride and some Lewis acid catalyst and heat it up with benzene, I'm going to end up with tert-butyl benzene. This is a Lewis acid catalyst, and it's acting the same way as we saw in bromination. So my Lewis acid is essentially ripping off the chlorine from this thing. I get this stable cation. This only works if I have a stable cation. This is it. And then that cation is attacked by benzene, just as we saw before. Pros and cons of this reaction. Pro, I got a new carbon-carbon bond. Does that make me happy? I'm not going to lie. Yes. But cons, I have a carbocation here. And we mentioned when we talked about SN1 chemistry that I kind of don't like carbocations. They can rearrange, for one thing. I often need a tertiary one. I can't really do this for a secondary. I certainly can't get a primary carbocation, right? So there's no way I could make something like that by a Friedel-Crafts reaction because I can't get a primary cation, right? So this requirement to get a carbocation is limiting, and I chafe at limits. A bigger problem that's maybe underseen here is that my product is activated. What do I mean? Well, this is an alkyl group, and alkyl groups are electron donating. So which of these reacts faster under these Friedel-Crafts conditions? It's this one, right? So I'm going to have a hard time keeping this from going on to making maybe a di-tert-butyl. I could even add more than that if sterics will let me, which I don't know that it will. But that's a problem, right? A, I don't like the carbocation. The carbocation can rearrange, do hydride shifts, this and that. I'm limited in what I'm able to add. And also, my product is actually a little bit more reactive than my starting material. Both of these products are solved by the Friedel-Crafts acylation. So instead of an alkyl chloride, I'm going to come in with an acid chloride. Otherwise, the same conditions. Some group here, some aromatic compound, and some Lewis acid, generally aluminum trichloride. Very, very cheap powder compound. Don't inhale it. It tastes like burning. But it's an efficient way to get at this stabilized acylium ion, right? And again, don't get it twisted when I draw O plus here. The O plus just reminds me that this carbocation here is stabilized by lone pairs on oxygen. Okay? So this is a very hot, great electrophile. This is going to come in and attack it, and this is my product. So I've solved all my cons, right? No rearrangement, all right? Because I have this nice stabilized carbocation, there's really no opportunity for me to do hydride shifts or any other kind of weird stuff. Even better, my product is now deactivated, right? Adding this carbonyl to it actually made it less reactive than the starting material. So I don't really need to worry too much about adding two of these things to the ring, because the second one's going to be a lot slower than the first one. So very cool. I still am making carbon-carbon bond, but now I don't have the problems of the normal alkylation.